Design and specification of the BITMONSTER code generation tool by Andrew Harris. Andrew?
Okay, hi, hello everyone. I just want to say I'm happy to be here in California, even though it's raining. The hills are just so green and beautiful. I haven't seen that in a while, so it's really beautiful, and I'm happy to be here, and I'm happy for all of us to be together. So, and thanks to the organizing committee for setting this up. So my name is Andrew Harris. I'm a flight software developer at the Johns Hopkins University Applied Physics Lab, and I'm going to talk today about a code generation tool that we built for the DART program. So well, first I'll just say, a lot of people ask me why it was called BITMONSTER, and I'll just say that the idea came based on, and I'll show you, but this is a serialization and deserialization system, and it takes data format definitions, and it generates C code that's pretty fast. And I just thought it was like Cookie Monster, you know, eating cookies and having cookie crumbs flying all over the place. So that's why I called it BITMONSTER. So it's a part of a tool chain. Our tool chain is Kaitai based, and Kaitai is an open source data definition language that you can look up online. And we use it at APL to manage our data definitions. So we can define structures in this language, and we can generate, using this tool chain, C code, executable C code that consists of basically a C structure definition, as well as serialization and deserialization routines. We have quite a few data definitions, as I'm sure you can imagine, and the actual, I'm not going to talk about that tool chain today, but you can hear a talk from 2019 talking about kind of the high-level goals of that tool chain from my colleagues Andrew Badger and Sam Biebelhauser. So in their talk was explaining how we can use those same data definitions to generate Wireshark Lua plugins to help us analyze messages on SpaceWire networks. So we can generate a variety of products from these data definitions, including C code, these Wireshark plugins, as well as some of our ground system products. So BITMONSTER is a second generation code generator. We started with one that we built in 2019, and maybe in the same context of the talk about from Marek yesterday about the time and space partitioning, this was the first time we had tried something like this, where we were generating, defining data definitions in text like this and generating C. And we weren't sure about the best way to go about it and what types of features that the Kaitai data definition language, which ones we would need. So we wrote a generator that was quite flexible and supported a variety of the things that the actual Kaitai language supports, like conditional deserialization based on a field at the top of a message structure, for example. But that generator was flexible and powerful, but we noticed that it might have some performance issues. And so basically, we looked at it, and I talked to Chris, who was the flight software lead at the time, and I asked, maybe, can I try writing a generator that might be faster in the case we do have an issue later on? And Chris said, sure, go try it. So I did. And so this is a talk about that, and specifically about the specification and verification of the tool as well. So it's actually significantly faster than the original one, 4 and 5 times faster, even up to 10 times faster. But it has limitations in that it only operates on a simple subset of all of the message definitions that we could create. And so kind of one of the things we realized, though, as we went on, much like Marek mentioned yesterday, is we realized that a lot of the structures we defined were pretty simple. They were straight linear structure definitions, and so BITMONSTER was usable for quite a few of the message definitions. I will say that we developed it on DART, but we didn't actually end up needing to use it on DART. So we as we saw, we did have an occasion to try using it, but we noticed that even for a small subset of messages, about 20 or 25 carefully selected ones, we could shave off about 3 or 4%, I think, of CPU margins. And this was near INT, integration and test. But we decided not to use it because we didn't need those 3 to 4% at that time. So since then, BitMonster has become the default generator for our current missions for IMAP and Dragonfly as well at this time. So I just want to say that a primary motivation of this talk, again, is to show you the specification and verification of this relatively simple algorithm in the hopes that if you have a simple algorithm that you want to test, maybe you can get something from this talk. It doesn't have to be serialization or anything like that. And even afterwards, if you have a question about a particular way to maybe specify your problem or something, I wouldn't, don't hesitate to come and say hello. So we're gonna define a specification, and we're gonna specify what BitMonster should do through a couple of properties. We'll define those on a couple of slides, and show you a testing framework that we can use to link that specification with the verification process. So the BitMonster code generator is the operations in yellow here in the 2 arrows. So we start with a message format, and BitMonster defines a set of expressions in a domain-specific language that includes just a handful of operations that you might expect to be useful if you're doing serialization. So and, or, shift left, shift right, and a constant operator. If you're not familiar with the term domain-specific language or DSL, you could think of this as kind of defining a virtual machine with just those operations. So a very simple virtual machine. BitMonster, the work of BitMonster is to actually to read in that message format and generate a sequence of instructions for that virtual machine. And that is arrow A to B at the top. So that's the message format to the domain-specific language. And I consider that to be the non-trivial step of our BitMonster. And the yellow parts, again, are the parts that are actively involved with the code generation. The white parts are important for the verification side. So what we can say is we can make a few assumptions. We can say that due to the simplicity of that domain-specific language, it's only got those 5 instructions. We can say that the transformation between the expressions in that domain-specific language and equivalent C expressions is trivial. So if we have a sequence of these instructions that are just and, or, and shift, it's assumed, arguable, but it's easy to construct an equivalent C statement with those because there's kind of a one-to-one mapping of C operators with these operations. And because that domain-specific language is pretty simple also, an implementation of an interpreter for that virtual machine is also trivial to create. It's only got those 5 instructions. So since we can also say that, and that's B to D there, we can also say that since the interpreter itself is so simple, that we can make an argument that there's a correspondence in behavior between that interpreter and what we would see from the C code that we generate. Okay, so we have a non-trivial part at the top, which is basically the bulk of BitMonster. And then we have a series of triviality arguments here that can kind of give us a way to justify some of the ways we're using this verification framework. So I just wanted to give you an example of a message format specification. On the right here, you can see this is an example of a simple chi-type-based message definition. It's a structure with the name mystruct. It's got 4 fields in it, and the first field has a 6-bit width, and field 2 is 2 bits, and so on. And you can see that here in the example, and we'll use this example running through a few of the upcoming slides. So first, what I said was we were going to define a specification for what we want this code generator to do, and we're going to do that by defining two what we call properties. And you'll see in the end why we call them properties. But the first one we're going to create is one called the serialization behavior property. And we're going to take our 4-field structure, and we're going to say, how do we want to define what the serialization is going to do? So if we take that structure definition and we take 4 initial values for fields in that structure, let's say field 1 has a value of 59, and field 2 has a value of 2, and we have 7 for field 3 and 4 for, or 21 for field 4. And we assume that we have arbitrary precision arithmetic in our test framework, not in the generated C code, but in our test framework. We can basically define what we want the bit pattern to look like by evaluating a simple function where we take the value 59, which was the field 1 value, times 2 to the 10. So we're basically shifting it by 10 bits. And then we add the value of field 2 and shifting it by 8 bits. And then we add 7 times 2 to the 5th plus 21. And you can see that the coefficient of each of the monomials here corresponds to the field values. So we have 59, 2, 7, and 21 that match the initial values. And the exponents of this equation here are just a simple transformation to the field positions in the message format. So for example, field 4 is 5 bits long, and it's at the end, so you don't have to shift it left by anything. So you can just see the 21 there. And I'm sure you can see that field 3, you can shift it by 5 bits because field 4 consumes those 5. So we can make an argument that this polynomial, or evaluating this polynomial, is fairly trivial. And so what we can do is we can say that this polynomial serves as kind of like an oracle for our serialization behavior. And so if you're trying to implement an algorithm and you want to try and make some stronger verification claims against your algorithm, one of the things you can try to do is figure out one of these oracles, or it's a kind of a trusted version of your algorithm. And if you can find a simple one of those that you're kind of convinced, yeah, that seems, I can't have made an error in that one, and you can convince your colleagues of that, then it's a good property. So we'll consider this for this example here as an oracle, and we do for the actual BitMonster as well, for how we want this, basically the machinery that does the bit shifting and such to work. So the second property, so that was the first one. The second one is kind of a symmetry argument, saying if you serialize your data stream and then you deserialize it, you can say that the initial values are the same as the values that you get out at the end. And we'll say that's our symmetry property. So now we've got 2 properties that we've defined, and we'll say that these 2 properties kind of represent the desired behavior of our C code, and we have some triviality arguments that I showed that produce a mapping well, we'll see it in the next slide, but basically we say that those 2 properties represent our specification for how BitMonster should work. And so now I just want to show you, once you have a couple of properties, or perhaps more, or even just one, how can you use, what kind of test framework can you use to link those 2 together? So, or how can you, I guess I'll first talk about how you can kind of perform a verification analysis in the particular case of BitMonster. So if you assume an initial set of values in a message format for the code generator, and we start here at the top. So for example, from our previous slide, we had that 4-element structure, and we had the values 59 and 2 and 7 and 21. We can take that message format and we can run the BitMonster algorithm and generate, as we said, a set of instructions in the virtual machine and get those serialization instructions. Then what we can do is we can leverage the interpreter that we built, and we can interpret those instructions and get a serialized byte stream as long as we feed in the initial values as well. So we can run the interpreter on the initial values and the byte stream on the serialization instructions and get a serialized byte stream. Then what we can do is, that's just a sequence of bytes. We can mush those bytes together and create an arbitrarily large size integer, because we have arbitrary precision arithmetic. And we can say that's an integer z. That's the result of running all the BitMonster machinery. And then what we can do is we can request the oracle. What does the oracle say the answer should be, which was that simple polynomial. And we can take the initial values in the message format and get a value q. And then you can ask, does q equal z? And that can be your first test result for the first property of how BitMonster should behave. For the second one, the symmetry property, we'll need to call BitMonster twice, but we start with a set of initial values again in the message format. And you can run BitMonster just like we did on the previous slide. We can run it and get a set of serialization instructions in that virtual machine, run the interpreter again and get a serialized byte stream. Then we can feed that byte stream into the interpreter again But we can run BITMONSTER first to get a set of deserialization instructions, which are masks and shifts, just kind of in the inverse direction. And we can run that to the interpreter and get a set of output values, y1 through y4. And then all you have to do is ask, does x1 through x4 equal y1 through y4? And that can be a check of the serialization symmetry. So then you can just mush those two tests together, and this is just a graph showing that. The yellow ones are for the serialization behavior property, and the cyan ones are for the symmetry check, and then just a couple of green arrows that are common to both. But now we have kind of a verification process here that can check both of those properties at the same time. And then what we can do is we can wrap that in a loop using a property-based testing framework, which is a framework that can help you out in running a wide number of tests on these properties. So you can kind of think of it as a kind of a Monte Carlo type system for algorithm testing or development. It gives you some tools for synthesizing a large number of randomized test cases. So for example, this testing framework helps us generate randomized sets of initial values, and also actually generates random message formats. And we can feed those in and run it repeatedly. And the testing framework also kind of wraps around the test result. And if these frameworks, and these frameworks exist for a wide variety of languages, by the way, there's also a feature in a lot of these that is a shrinking operation. So if it encounters a kind of an input sequence that causes a failure of the verification, the toolchain can try and intelligently reduce the size of that input vector in various ways to try and get at the smallest one that still fails. And then it can tell you, hey, you know, this one fails. And you can go back at your algorithm and say, why did that one fail? Well, +1 instead of -1, you know, or something like that. And if it can't shrink it, it just tells you the big one. But one nice thing is that it gives you a test case that says, hey, your properties are failing on this particular test case. So, yeah, one of the interesting things about this testing framework that I found was it kind of gives you a way of strengthening kind of a verification claim. It's in the sense that you can say for all message formats and initial values, the BITMONSTER serialization is correct according to our specification, so those two properties. It's not exactly there because it's limited to the random test cases that it can generate, so it's not, you know, it's not fully formally proven, but it's a step in that direction, and it's actually significantly easier to start this way and use these tools. In fact, I think I'm not a formal methods person, but I hang around a few of them once in a while. And, you know, I think one of the aspects is try first, if you're interested in trying something like this, try doing it in a property-based testing framework first before you try and do a formal proof of your algorithm. Because first of all, this is easier. And if you can't prove it here, you're never going to be able to formally prove it. So you have to make sure you're comfortable and you know it shows good success here before you ever try and even move to a formal verification. It also allows us to test BITMONSTER with message formats that we haven't defined or haven't thought of yet. So it gives us kind of a stronger claim for that. You know, on Dart, we ran BITMONSTER alongside our original algorithm or code generator and verify that they both passed the unit test sets. But with this framework, we were able to test BITMONSTER with even more message formats than we had for Dart. So that helps, you know, make an argument that in the future we won't have issues as well. It also allows innovation and experimentation. So if we get a new staff member or find a new way to implement BITMONSTER, perhaps have an additional optimization in the code generator, we can use this framework to give us confidence that we haven't broken something, and it just gives us more flexibility and more confidence in poking around and making changes. So I just wanted to say that, you know, I hope I was able to illustrate for you kind of a simple algorithm, which was this BITMONSTER system. I'll tell you that BITMONSTER itself it's actually, for all of this, it's less than 950 lines of Haskell. But so I just wanted to give you oh, thank you. I just wanted to say it is fairly simple, and so I found it instructive. You know, if you have a simple algorithm that you'd like to try something like this out on, you know, I hope you can get something from this talk. I showed a couple of properties, you know, that we can use to specify the behavior. Showed this property-based testing framework, and basically how it exercises the algorithm in the context of that specification, and basically shows you how you can strengthen your verification claim to expand to universally quantifying, you know, for all messages and for all kind of with those constraints of the sample space. And I just want to mention that it was written in Haskell primarily so that you could see the library that was used, the property-based testing framework. It's called QuickCheck. It's a Haskell library, but I say again that this has become quite popular, and it's available for a variety of languages now. So I suspect, I know there is one for C. I haven't tried it myself. I think it's called Theft. And I believe there's one for Rust as well, but it's quite popular. And so I suspect for your language of interest, you could find something like this. And I just want to say thank you. Thank you for the time.
Any questions?
Talk. Really interested in how you test out your verification. So you say that you generate a lot of random tests. Can you go into detail about what that is?
Well, sure. So BitMonster is a plugin to a larger this Kaitai toolchain. So we aren't actually generating random message formats, but we're generating kind of an intermediate representation from the toolchain. It's kind of a sequence of S expressions at times. So, but we are but they're equivalent to the message formats. So technically, we generate a large number of these randomized S expressions that represent message formats in a kind of a transformation, if that helps. And then initial values, the tool. So we wrote some generators, I think is the correct term, to generate these randomized message format definitions, and also the sets of initial values. It provides, you know, tools for producing random.
All right, thank you.
You're welcome.
Very interesting to hear about QuickCheck and in the talk here. We are using it too. About implementation in other languages, the inventor of QuickCheck, John Hughes, founded a company who made an Erlang implementation of QuickCheck, which is the most mature, because they are working on that for 15 years now. And that also supports C code. So it generates C code, so you can actually test complex C code. And they used it, for example, for automotive testing, for a complete AUTOSAR stack with complex models and everything. So this went far beyond. Of course, you're swapping then the weird Haskell syntax with weird Erlang syntax to write your property-based tests. But it's a commercial product, so it's not for free, but it is very advanced beyond what was done in Haskell.
Yeah, I'll have to stop by. Thank you for that information.
We do have a question online. For the specific case of serialization, deserialization, do you know how this approach compares to using protocol buffers or similar for generating the C routines?
Yeah, sure. So in terms of the difference, the Kaitai toolchain versus like protobufs, the thing we liked about, we looked at protocol buffers, but, you know, when we have a lot of custom avionics, as we all do, you know, we build software for computers that have a lot of, let's just say, custom peripherals. And these peripherals are kind of unique, and a lot of registers and interfaces that are very custom. So we wanted a data definition format that was very explicit in basically the wire format. And our investigation of protocol buffs was that, and I'm not an expert on protocol buffs, but I think was that you can define a format in protobufs, but protobuf can take it can actually it can change what's sent over the wire for reasons of performance, for example. You know, so it can actually make significant improvements and modify what the wire format looks like, and it's transparent to you because on the other side, when you read in your protobuf, it'll do the reverse transformations. But we wanted a definitional language that could specify exactly every bit in a register or a set of registers for these avionics, so that we could basically be confident that we could, bit bang those registers in the right way. So that was the reason why we kind of selected this chi typeface. It's very expressive and very specific for the specific bit patterns, and it won't. And our tools are designed not to change, not to do any optimizations there.
Very good.
All right,
Thank you, Andrew.
Yeah, thank you again.
Okay.